students. In the previous class, we have discussed about AC circuit, the basic concepts of AC circuit. Mainly we discussed about mean value of AC and RMS value of AC. And now we have to discuss in detail about different types of AC circuit. That is AC circuit connected with a single resistor, an inductor and a capacitor. And also we have to discuss AC circuit with all these three components together in a single circuit. That is a AC circuit with a resistor, inductor and capacitor. Our today's discussion is about AC circuit connected with a single inductor, an inductor coil. We can see here what are the effects of connecting an inductor in an AC circuit. What will be the phase difference in voltage and current when an inductor is connected in an AC circuit. Okay, all of you listen. Today I am going to explain AC through an inductor. AC circuit with an inductor coil connected in that. You can see what are the effect of inductor in an AC circuit. Here we have a circuit. You can see here there is an inductor coil connected in this circuit. It is having self-inductance value L, and there is a AC source. It is producing AC. It is producing an alternating voltage V equal to Vm into sin omega t, where Vm is the peak value of voltage and V is the instantaneous value. Every moment this voltage is changing. Vm is the maximum value of voltage produced in the generator. Suppose this is a small generator. It is producing an alternating voltage Vm into sin omega t. This Vm is a constant for a given generator. It depends upon the number of turns of the armature coil, area of the coil and the material of the core used inside the coil, and also the angular velocity omega of the armature coil. Okay, here omega is the angular velocity of the armature. When the generator rotates, the armature rotates, its angular velocity is here omega. That will be a constant for a generator. Usually a generator will rotate, the armature of a generator will rotate with a constant angular velocity. Omega t is the theta. Angular velocity into time will give the angle turn, that is theta. Okay, so this is the circuit. Here in this circuit we have only an inductor coil and a source of AC voltage. There is no ohmic resistance. There is no resistance in the circuit, only inductor and AC source. And first of all we are going to apply Kirchhoff's rule for this closed loop. When we apply the loop rule of Kirchhoff's loop rule for this closed loop, according to Kirchhoff's loop rule, the algebraic sum of EMFs and the product of current and resistance in a closed loop must be 0. Here we don't have any resistance in this circuit. We have two EMFs here. One EMF, one voltage is the voltage produced by the generator, that is Vm into sin omega t. Another EMF is induced in the coil because of its self-inductance. Due to the self-inductance, an EMF will be induced in the coil, that is given by E equal to minus L into di by dt. Minus L into di by dt. So we have two EMFs here. One is the EMF applied voltage, that is equal to, that is V is equal to, instantaneous values V is equal to Vm into sin omega t. Vm into sin omega t. The another EMF is induced in the inductor because of its self-induction, that is minus L into di by dt, minus L into di by dt, where L is the self-inductance of the coil. L is the self-inductance of the coil. That also is a constant for a given inductor. It depends upon the number of turns, area of the coil and also the material of the core used inside the coil. So when we apply Kirchhoff's rule for this closed loop, we can write the equation like this. The total EMF, the total voltages are Vm into sin omega t, and plus we can minus because there is minus L into di by dt. Minus L into di by dt. This algebraic sum total should be 0. Okay, so I can write L into di by dt is equal to L into di by dt is equal to Vm into sin omega t. Vm into sin omega t. Okay. Now if I take this L to right hand side, the self-inductance value to right hand side, it will go to denominator here. So the equation becomes di by dt is equal to Vm by L, Vm divided by L into sin omega t. Vm by L into sin omega t. Again I am taking this dt to right hand side. This dt if I am taking to right hand side, it will come to numerator. So the next equation becomes di is equal to Vm divided by L into sin omega t into dt. This di is very infinitesimally small value of current. Now if you want to get the expression for current in the circuit, we can integrate this equation. When we integrate this equation, we will get the current. The current I is equal to, integrating this equation, integral Vm by L into sin omega t dt. Okay. When I integrate this equation, here Vm by L is a constant. That can be taken outside the integration. Vm by L, both Vm and L are constant. So Vm by L can be taken outside the integral. So the next equation can be written as I is equal to Vm by L, I am taking outside the integral, then integral sin omega t dt. Sin omega t dt. When we integrate sin omega t dt, that is sin omega t is a trigonometric function. When we integrate a trigonometric function, if there is a constant inside, this omega is a constant here, then the result of integration become 1 by omega into sin omega t is minus cos omega t. Integral of sin omega t is minus cos omega t. So this integration result will become 1 by omega minus cos omega t. 1 by omega minus cos omega t. So the next equation can be written as I is equal to, that is instantaneous value of current is equal to Vm by L sin omega t integral is 1 by omega into minus cos omega t. 1 by omega into minus cos omega t. Now we can apply a trigonometric identity, that is cos theta can be written as sin 90 minus theta. Sin 90 minus theta. Or we can write cos theta is equal to sin 90 is pi by 2. Pi by 2 minus theta. When we apply this identity in this equation, when we apply this identity for this cos omega t here, okay, we can write the equation like this, that is I is equal to, current I is equal to Vm by L omega, okay, and cos omega t we can write sin pi by 2 minus omega t. There is a minus sign here, so minus into cos omega t I am writing sin pi by 2 minus omega t. Now when I multiply this minus sign inside, this pi by 2 become negative, and minus into minus omega t become positive. Omega t become positive. Minus into minus plus omega t become positive. So the equation can be written as current I is equal to Vm by L omega, Vm divided by L omega, then sin pi by 2 minus omega t become sin omega t minus pi by 2. When the minus is multiplied inside, become omega t minus pi by 2. Okay. Now in this equation, you can see here, it is the equation of current, just like Ohm's law equation I equal to V by R. And the sine function is showing the variation of current, instantaneous variation of current. So the peak value of current we can obtain from Vm by L omega. It is just like I equal to V by R. So this equation, Vm by L omega can be written as Im, the peak value of current, Im. In this equation, if you consider this as just like the Ohm's law equation I equal to V by R, the position of resistance is occupied by L omega. The position of resistance is occupied by L omega. So this L omega we are giving a new name, that is L omega is equal to XL. The symbol is XL, subscript L. It is called inductive reactance. It is called inductive reactance. Inductive reactance. And this inductive reactance XL, that is XL equal to XL equal to L omega, and we know that omega is equal to 2 pi f. Omega is 2 pi into frequency. So XL also can be written as XL equal to L into 2 pi f. L into 2 pi f. So it means XL is same like resistance. It is occupying the position of resistance just like I equal V by R. So the effect of L omega or effect of XL is same like that of resistance. Same like that of resistance. Its unit is ohm. It is measured in ohm. It is measured in unit ohm. SI unit of XL is same ohm. XL is called inductive reactance. Its unit is ohm. It is just like resistance. XL is same like resistance. Its effect is same like that of resistance, measured in ohm. Only the mode of action is different. Usually if there is a resistor in a circuit, it will oppose the flow of current. So current will decrease in the circuit, and that resistance normally it decreases the current in a circuit due to the internal friction when the electrons flow through the material. But here in an inductor coil, XL is the opposition of flow of AC through an inductor coil, and that opposition is not because of the internal friction, it is because of the reverse EMF. The reverse EMF induced in the coil due to self-induction. So mode of action is different, but effect is same. Physical effect is same, mode of action is different. So it is measured in the same unit of resistance, ohm. Okay. So this equation, the final equation of current, we can write down now here. The equation of Vm by L omega. Vm by L omega can be substituted as Im, peak value of current. So the equation of current we obtain like this. Equation of current is I is equal to Im into sine omega t minus pi by 2. Okay, now we have two equations here, two equations of voltage and current. You can see here the first equation, the equation of voltage in the circuit, it is given by this V equal to Vm into sin omega t, means the generator is producing, okay, this generator is producing a voltage. It varies according to this equation, V equal to Vm into sin omega t. And the same time the current in the circuit obtaining like this, I equal to Im into sin omega t minus pi by 2. I is equal to Im into sin omega t minus pi by 2. So what we can see here in these two equations, what we can see here, voltage is Vm into sin omega t, current is I equal to Im into sin omega t minus pi by 2. It means when a current flows through the circuit, voltage will be ahead and current will be coming behind. Okay, current is lagging behind the voltage by an angle of pi by 2. It means when the voltage is maximum, current will not be maximum, current will be 0. Okay, when voltage is 0, current will be negative maximum, negative side. It means when an inductor coil is connected in a circuit, always current will be lagging the voltage by an angle of pi by 2 90 degree or pi by 2 radian. That is the effect of inductor coil connected in AC circuit. So in an AC circuit, if you are keeping a wire twisted, always that wire will have an inductance effect. Because of that, current will be lagging behind the voltage in an AC circuit, and it has lot of other effects also we will discuss in coming lessons. Okay, now we can see the graphical representation of this voltage variation according to this equation and current variation according to this equation, and also the phasor diagram of voltage and current in an AC circuit with an inductor coil. Okay, we can see in next page. Okay, so we have the equation of voltage given by the AC sources. V is equal to Vm into sin omega t, and current equation we derived, I is equal to Im into sin omega t minus pi by 2, equation of current. In this equation, Im is actually peak value of current we obtain from Vm by L omega. This L omega is called inductive reactance. It is given a symbol XL. So Im can be also written as, peak value of current also can be written as Vm by XL. Vm by XL. Okay. XL equal to L omega. XL is equal to L omega. Also XL is equal to L into omega is 2 pi f. So it can be written as 2 pi f also. Okay. Now when we represent this variation of current and voltage on a graph, suppose I am drawing a graph here. On x-axis we can take the theta angle omega t, and y-axis we can take either voltage or current. Voltage or current on y-axis. So y-axis I am taking V, instantaneous value of voltage, or current on y-axis, and x-axis I am taking omega t, theta equal to omega t. Okay, and first we will apply equation V equal to Vm sin omega t. We can see the variation of voltage, the sine wave of voltage in this case. When we consider the rotation of the armature coil of a generator, here omega t is the angle. Here omega t is the angle between the direction of magnetic field, and normal drawn to the plane of the armature coil. Okay. So if initially when we consider like this, there are two magnets, north pole and south pole, and armature coil is in between these two. Suppose this is the armature coil. This side is north pole and this side is south pole. So the direction of magnetic field is this way. Direction of magnetic field is this way, north to south. This is the direction of magnetic field. And normal drawn to the plane of the coil also same direction. So here initially theta is equal to omega t is equal to 0. Okay, that is the angle between the direction of magnetic field and normal drawn to the plane of the coil is 0. Suppose the armature is starting the rotation from this point. Then we can take here in this equation omega t equal to 0. If omega t is 0, sin 0 0, V will be 0, means the voltage will be at this point, at the origin, at 0 here. Okay. At the same time, when we apply omega t value in the equation of current, omega t equal to 0, then here there is a minus pi by 2 remaining, then become minus sin minus pi by 2, that become minus 1. Minus 1 into Im is minus Im, means current will be negative maximum. Current will be at negative maximum here. Suppose current is here at the negative maximum. That is equal to minus Im. Minus Im, peak value of current in the reverse direction. It means when the voltage is 0, current is negative maximum. Okay. Now again suppose the armature started rotation and it rotated 90 degree. Suppose the first half rotation, this armature rotated 90 degree. Then omega t become 90 degree, pi by 2. Sin 90 is 1. V become Vm. Means voltage gradually increased to maximum. When the armature rotates 90 degree, voltage reaches maximum. So this angle is pi by 2. This angle is pi by 2. At that point voltage become Vm, peak value of voltage. And at the same time, if you apply that value, that is theta is equal to, first we applied omega t is equal to 0. Then we applied omega t is equal to pi by 2. When we apply omega t equal to pi by 2 in equation of current, here omega t equal to pi by 2, then pi by 2 is 0, sin 0 is 0. What happens here? Current will increase from negative maximum to 0. Negative maximum to 0. So at pi by 2 angle, current is here. Okay, voltage is here. Always current is coming behind the voltage. The next angle, if I apply omega t equal to pi, omega t is equal to pi, that is 180 degree. What happens here? In the first equation of voltage, V equal to Vm into sin 180. Sin 180 is 0. So voltage again become 0. Means the voltage will reduce to 0 again. Voltage from the peak value, from maximum value, will gradually become 0 here. Here the angle is pi radian. But at that same time, if you apply pi in the second equation, omega t equal to pi in the second equation of current, omega t equal to pi minus pi by 2 is pi by 2. Pi by 2 means 90, sin 90 is 1. Means current become maximum. So the current at the angle pi, the current will go to maximum value this way. So here current become maximum. Current is gradually increased to maximum value here. So what we can see here, next time the omega t value 3 pi by 2, then 2 pi. What we can see, the voltage and current will be changing like this. Voltage will go this way. Voltage goes this way. And current will be lagging behind that. Current will be lagging behind that this way. Okay. So always there will be a difference of phase difference of pi by 2 between voltage and current. Here this angle is 3 pi by 2 and this is 2 pi and so on. Okay, this will be keep on changing. So the voltage and current will be varying according to these two equations. Current is always coming behind the voltage. Current is always coming behind the voltage. Now the same way when we draw the phasor diagram for this variation of voltage and current. Okay, here the voltage phasor I am taking here. This is the voltage phasor of voltage. This represents the peak value of voltage and current is 90 degree behind that this way. This is peak value of voltage. It is at an angle omega t. Phase angle is omega t with the x-axis and y-axis. Okay, and you can see here the current is, this one is current, peak value of current. This is peak value of current, and here you can see between voltage and current there is a 90 degree phase difference. Current is behind the voltage by 90 degree pi by 2. Current is coming behind the voltage by 90 degree pi by 2. And also you know that phasor always rotates in anti-clockwise direction. These two phases always rotates in anti-clockwise direction this way. When these two vectors rotate in the anti-clockwise direction, you can see always current will be coming behind the voltage. And during that rotation, if you take the projection of this Vm on y-axis, means the component of Vm on y-axis at any instant of time, that will be the instantaneous value of voltage. Same way, the projection of Im on y-axis at any instant of time will give the instantaneous value of current at that time. So when these two rotates in anti-clockwise direction, the voltage and current will vary according to this given graph. Okay, this way we can represent the variation of voltage and current in a circuit connected with an inductor coil in AC circuit. Also, when we see the equation of inductive reactance, that is XL equal to inductive reactance resistance offered by the inductor to the flow of AC, XL equal to L into 2 pi f. This L into 2 pi f means it depends on frequency. For a given inductor, L is constant, 2 pi is constant, only frequency of AC is the variable. So for all AC, the inductor coil will not offer the same opposition. The opposition to the flow of AC given by the inductor coil, it depends on the frequency also. That is why it is called inductive reactance. Normal resistance depends upon the ohmic resistance, depends only on the length of the wire, area of cross section, material, temperature, etc. So for a given material, for a given length, it will be constant. But inductive reactance XL, it is not constant for a given inductor. It depends on the frequency of applied AC also. So when we draw a graph, by taking the frequency on x-axis and inductive reactance on y-axis like this, frequency on x-axis and inductive reactance on y-axis. When we draw the graph like this, suppose I am taking here inductive reactance XL on y-axis and frequency of AC on x-axis, and if I draw the graph, since from this equation, since L is constant, 2 pi is constant, this equation we can write XL is directly proportional to frequency of AC. So we'll get a linear graph. Like this. The graph will be like this. The inductive reactance increases with the frequency. The XL value is directly proportional to frequency, so it increases with the frequency. So high frequency AC will experience more opposition in an inductor than a low frequency AC. And if you consider a DC in an inductor circuit, if a DC is connected, for DC there is no frequency. Frequency of DC is 0. For DC current, frequency equal to 0. So XL will be equal to 0. XL equal to 0. It means when an inductor is connected in a DC circuit, there will be no effect at all. If an inductor is connected in a DC circuit with a battery like this, with a cell, this inductor will have no effect in the DC circuit. It will act just like a wire. It will act just like a normal wire only. This inductor will act just like a wire in a DC circuit because DC frequency is 0. Frequency 0 means XL 0. No inductive reactance. So there will be no lagging or leading of current. Means an inductor can act only in AC circuit where the current is varying, keep on changing. Okay. So inductive reactance is directly proportional to frequency. When frequency increases, inductive reactance also will increase. It means that a high frequency AC, it will be difficult to flow through an inductor. A low frequency AC can easily flow through an inductor. And if it is a DC, no inductive reactance at all, DC can flow without resistance, without any opposition through an inductor coil. So these are the main points related to the flow of AC through an inductor in a circuit. So main points once again, when a current is AC current is flowing through an inductor circuit, voltage and current are not in same phase. There is a phase difference. Current will be lagging voltage, current will be lagging behind voltage by an angle of 90 degree or pi by 2. Okay, and also the inductor will offer a resistance, an opposition to the flow of AC. It is called inductive reactance and it has given a symbol XL. It is given by XL equal to L omega or L into 2 pi f. And that XL value directly proportional to frequency of AC. High frequency will experience more XL value and DC circuit XL will be 0. And also the phasor diagram, waveform of voltage and current in AC circuit fitted with an inductor circuit. And also the graph representing the variation of XL, inductive reactance with the frequency. These are the main points of discussion. Okay, thank you.